Okay, so you wanted to talk about chapter 12 today.
Yeah, I'm not too sure if you want to include that into curriculum because I don't remember learning any of that in
Me
my
neither.
Chem class at all.
Yeah, I know. I don't. You know what? I think back to when I first took general chemistry, and I don't remember any solid state. And it's easily the part of chemistry that is the most mysterious to me. As I was thinking about it today, I was looking through and I was kind of working out some of the things that we could talk about. And I thought, only a chemist could love this stuff. That that if you love chapter 12 on the solid state, I don't know what you think your major is, but you're supposed to be a chemist. Maybe you could be a physicist, but it's just not. There's so many fine details that it's not clear how that matters to the rest of the world at all. And there's mathematics going on in there. There's geometry going on in there. There's waves and trying to figure out wave equations going on. There's just a lot of stuff. And if you love it, you're a chemist. So, yeah, I'm mediocre at best. When it comes to solid state, I am definitely less than mediocre. So, but there are some things that I think can be a little interesting, very interesting if you're a chemist, a little interesting to other people who might have some intellectual curiosity left. And if you've got some left in week number, whatever it is, 15 of those courses, more power to you. Gases, it's easy to get behind. Everybody teaches gases. Liquids we can see those and we can interact with those, and solutions, there's lots of relevancy there. But I think the point of solid state is that we're going to use some mathematical techniques. We're going to use some very cool scientific breakthroughs to try to get an understanding of where atoms are in the solid state, how big they are, really how small they are, and then some ideas about how they interact and how they react. That's basically what the point of chapter 12 is, to get some understanding of that in the solid state. So let me show you some things that I was able to figure out, and I'll point out some of the pieces that are a little bit insightful. The type of thing that they are trying to lead students through is looking at the way atoms pack together and figuring out something about how big these individual atoms are based on some mathematics, based on how they pack together. And they give us 3 general ways in which they pack together. I'm going to show you some screen captures of them that I took earlier on today. So this is a simple cubic cell. And basically, it is trying to show that one way atoms pack together is you have these 4 atoms that are all touching each on a face. The first one is, can you see that?
Mm-hmm.
Simple cubic. And simple cubic, I can show pretty easily. I found some coins. No carrots today, at least not yet, unless we decide carrots are going to be that much better. And so simple cubic, the atoms can pack together in the closest they can get together is on one face. It will look like I packed these dimes together. It's not offset like this. They pack together nice and simply like this. And so if our goal is to try to understand where the atoms are, well, this tells us a little bit about where they are in relation to each other. But we're also going to try to do a little mathematics to figure out how big they are. And so when it shows you something like a simple cubic structure like this, what they're saying is, hey, if we could measure this distance to this distance, because they're touching, that tells us the diameter of any particular atom. And so they're going to take you through a whole load of mathematics that basically says, hey, if we can figure out what arrangement they have, in this case, simple cubic, and then we can figure out what the distance is from the center of one atom to the center of another atom, then that can tell us that's the same as the edge of one atom to the edge of one atom. And so this distance from here to here is the same as this distance from here to here. And so we can figure out how big they are. So we are going to use whatever they can tell us, or whatever we can get from experiments that will tell us what is the arrangement. And then we're going to use some other experiments to tell us how big they are. And so that's where, that's what the various parts of the text are trying to lead us through. So in this simple cubic one, they're showing, here are my 4 dimes, 1, 2, 3, 4, right? All on the face of this cube. And they're saying that if we play our cards right, we can use some mathematics on this to figure out how big those atoms are. And they start with, hey, it's a cube, and it's got a bunch of radiuses, right? And it's got a bunch of diameters. But that is the most simple mathematical piece that we're going to get. Okay, so here is a simple cubic shell trying to show that we've got 1, 2, 3, 4 atoms on the corners of this unit cell, and behind it there are another 4, which I couldn't show with my dimes very well. Oh, sorry, I didn't mean to do that. And if I click on reset here, it brings up a bunch of them together. Oh, let's see if I can stop it. So here's 1, 2, 3, 4, and behind it are 1, 2, 3, 4, and you might be able to begin to see that in this simple cubic arrangement, here's my 1, 2, 3, 4 dimes. Behind it are 4 others. And if we just look at an individual, what's called a unit cell, we can begin to anticipate and begin to calculate, okay, if I know that I have this atom touching this atom, then the radius of that individual atom is halfway between the distance, kind of like we had with these 4 dimes. Okay?
Mm-hmm.
The mathematics for this is very, very, from my perspective, pretty simple. You're going to say, hey, if I can figure out how far apart these are, then I can, how far it is from center to center, then I can figure out what the distance, what the diameter and what the radius of any particular atom is. Okay, so now let's switch to a slightly more complex one. Okay, so the next one I'm going to do is face-centered cubic. And so what it's trying to show is that we have a similar sort of 1, 2, 3, 4, but there's another atom that is tucked on the face here. So if I go to back to my dimes again for a second, or maybe we'll use nickels this time, since I have some nickels here. Instead of being simple cubic on the face, there's a 5th one in there. And my nickels don't fit together quite the way the dimes did. But so we have 4 on the corners and 1 on the face inside. So this is called face centered cubic. Okay? And so if it's face-centered cubic like this, and I'm trying to find out what the size of my nickel is, I can't do it the same way I did before, because these two aren't touching each other. The only ones that are touching each other go through this diagonal. And so now you have to do a little bit more complex mathematics, which is to say, hey, if I know what this distance is here, and I know what this distance is here, then I'm going to use Pythagoras. The Pythagoras theorem of A, B, and then through the diameter C. So I know that A squared plus B squared equals C squared. And so it leads you through solving this equation to try to find out what is the distance from here to here. And if I know that distance, then I know, oh, okay, so I've got half an atom, I've got a whole atom, and I've got another half atom to get to the center. So this distance here is the length of 2 atoms, or the diameter of 2 atoms. And so if I know that it's face-centered, then I do a slightly more complex mathematics, and I can figure out that the size of these atoms is determined calculating through across the diagonal of this face. So in simple cubic, I could do it almost by looking at it and saying, hey, look, here is, if this distance is A, this distance is A, then I know, frankly, the size of my atoms is A. I can handle that. But here, because of the way they're packed together, if I know the distance between these 2 atoms, and I know the distance between these 2 atoms, then I can calculate the diagonal, and then that diagonal will tell me something about the size of the individual atoms. How am I doing?
Okay, that makes sense.
So that's for face-centered cubic, and then everything's gonna go crazy here for a second. The third kind of packing is called body-centered cubic. And body-centered cubic, okay, so body-centered cubic, you can still see the atoms on the corners all the way around, but rather than having this center one on the face, it's actually buried in the middle. And you might be able to see that as I rotate it just a little bit, that it's in the center of that cube. So now, if I'm trying to figure out what's going on with, if I want to find out how big any one of these ones are, I can't go from corner to corner. I can't go across this diagonal because they're not touching. I have to go through the center of the cube. And that requires just a hair more complex mathematics. I bring up my preview again. So if I go to body-centered cubic, which is this one. So these 2 on the corners aren't touching. It's also not touching this one here or this one here. The only way they're touching is going through from this one through to the one that's in the center and through down to this one on the far corner. And so it's a lot harder to show that with coins, especially since my coins won't stack, but I found some quarters. Hopefully let me bring that one up again. I stopped the share. So body-centered cubic. There's some down on the at the bottom layer. Here's my one that's body-centered in, and then if I try to put these ones on top, it doesn't work so well. I think I ran out of quarters. Oh, here's a couple quarters, I think. There's a quarter. Canadian quarters, look at that. Oh, not even, but in order to try, see now, it's so hard, it's hard to see this one, right? But trying to understand which ones are touching requires me to go through the diagonal of the whole unit cell. And so that's why trying to understand the mathematics of how big these atoms are gets more and more complex as we add, as their packing structures gets more complex. Ask me a question, Kevin. Was there anything that I just showed you that seemed to make sense to you?
I think I can understand the different cubics, I think the coins kind of helped.
Okay.
Maybe not so much with the body-centered cubic
Yeah,
because
they stink for that.
yeah, the three-dimensional, they're
Yeah.
more flat than round.
Yeah, I know. And then they tip off the top, right?
Yeah.
Pretty much horrible.
But is this just some of the basics that the student should kind of understand for solid states, or?
We're going to look at crystal structures, and we're going to ask students, tell us how big a silver atom is. Calculate how big a sodium atom is. From looking at some sodium chloride, or looking at some sodium or solid sodium, or some solid silver. And we're going to say something like, we're going to let you know, hey, when it's a body-centered cubic solid, or it is a face-centered cubic solid. And so when you're given that information, you're going to be able to use the packing structure and some information about how far apart the crystals are, how far apart the atoms are in the crystals, to figure out how large the atoms are. I mean, pretty much a miracle, basically. I mean, these are smaller than I mean, it's unbelievably small. So small that we can't really even comprehend how small they are. And yet we're going to tell you down to like 10 to the minus 9, 10 to the minus 10, how big they are, right? That's pretty incredible. So if you can begin to see that different shapes and different packing structures will require slightly different mathematics to solve the size of the atom. Then when we teach you the technique for determining the distances between the atoms, the distances between the atoms, it'll make sense that you're actually doing something that is physically, cosmologically valid, so to speak. That it's not just completely made up. Yeah, I can see that's a little unsatisfying for you.
No, I think that's fine. I think it might not be very practical to know the size of an atom in most solids in your everyday life, but like you said earlier, it's interesting for chemists, for physicists, and I guess if you have a little bit of curiosity. So
yeah.
This is just a good first step,
trying
to understand.
I mean, this is a place in this course where anybody that is going to be successful, you've got two choices, basically. You can memorize probably 15 or 20 things, and you can answer every question. But if you can get some understanding of some geometry, you get one piece of understanding of waves, and you can get 2 or 3 pieces of understanding of how they pack together, then you're not memorizing anything. You're using it, you're living it, and it becomes part of your scientific, technical repertoire. So you basically have a choice. You memorize like 15 different things, get through the questions, or 2 or 3 bits of understanding, which I think are within people's grasp. This is just one step beyond high school level math, one step beyond high school level science. It is just a nice next step in our intellectual scientific progression. So people can do this. Almost everybody in this course can do this. Probably everybody. A little bit of work.
Okay. Thank you for that little intro to solid states, though. That was kind of nice.
All right. Thanks, Kevin. I appreciate the compliment. All righty. All right. Thanks, Kevin. Talk to you next time.
Talk to you next time, Dr. Hunter.